you a chance to ask me questions. I'm just letting you know that I'm recording this now. So what I want to do before I start, obviously I've got some things I can talk to you about, just a few odds and ends where I think just need little reminders here and there. And I'll give you a few tips and maybe a bit of a masterclass on combining topics. But what I thought I'd do really before I do that is, rather than me sort of deciding the agenda for this lesson, I thought it'd be much more useful if you could tell me what you would like me to go over and what you'd like me to help you with. Obviously, the more you do, the more you ask me, the more I can tell you. And if you tell me honestly that you're struggling with a particular topic, obviously that means I can give you proper help. So does anybody have anything they want to ask me about?
Gary, I thought we were meant to submit the papers tomorrow.
Sorry?
The practice paper 5, I thought we were meant to submit it tomorrow.
Yeah, that's the final deadline for it. But this particular lesson now is really sort of a bit of active revision with me, so that you are actually getting some proper live lessons. Otherwise, it's just wall-to-wall practice papers, which is useful, but I'd rather not sort of inundate you with papers and nothing else. So, I mean, does anybody have any questions? Any particular topics you'd like me to talk about or show you, or if there are particular types of questions where you found it really difficult? No, I see you've all actively turned your microphones off there. So what I'm going to do is, and I hope I'm not just talking to myself here, I'm sure I'm not, I'm going to talk to you a little bit about vectors. I think we started on some work with vectors over the last sort of, in the last sort of revision lesson. And what I got back from many of you was that you kind of get the basic idea about vectors, but I think sometimes the application of vectors gives you a lot of trouble. We talked last time about components of vectors. I'm going to talk to you a little bit more now about resolution of vectors and some examples of the sort of things you might have to do. So I'm going to make a start on that. So I'm going to switch my camera to my desk camera. There we are. And what we're going to do is I'm going to show you a few examples. I think probably the best way to really to explain this topic is really just to do examples. So imagine you've got, is this a classic one? It comes up every couple of years or so. Got an object on a slope. So, for example, if we have this object on a slope, it's stationary, and what you do is you can do some calculations to work out the force of friction and so on. To look at why this object with a particular mass, m, is stationary, what you need to do is to resolve the force vectors. So we've got to establish which forces are actually present on this sort of block here. So the obvious one, we're on planet Earth, so there's going to be that wonderful thing, gravity. That's the weight of the object pulling it down. So I could draw on here the arrow. Well, the weight would act from the center of gravity and would act downwards. Okay, so that's one force that's acting. Now, if we think about it, there's a component of that force that's going to be in this direction here. So without something stopping it from sort of going without stopping it from sliding down the slope, we need another force which is going to stop it. Well, if that block is sat on the slope, then there's going to be a force of friction. And that force of friction is going to be going up the slope. Okay. Now, if we've got this particular slope and that's our force of friction, if we look at just those two vectors, clearly it wouldn't be in equilibrium because there's still a net force downwards. So what's actually happening is that this slope or this ramp is reacting to the force from this block. So the reaction force is what we call the perpendicular reaction force of the plank is always at right angles to the surface. So if I drew this, say, over here, this would be the perpendicular reaction force on the block caused by the fact that it's sitting on the ramp. So if we know this angle, we can actually start to resolve vectors. And the way that we resolve vectors, if this is in equilibrium, write that down. If it's in equilibrium, then the sum of all the forces in all directions, that symbol there means sum, of all forces in all directions equals 0. If that's the case, then it's like any other vector. You might remember when we talked about sort of walking around, and introduced vectors. Those of you who were here for the vectors lesson, if we think about it, if I walked, say, 10 meters in that direction, and then I walked 5 meters in that direction, so 5 meters, yeah, counts that correctly. Then what I've done is I've got a net sort of displacement, which would be in this direction, my resultant displacement. Okay, and I could actually work out what that is. It's a physical, in terms of the magnitude, it's the physical distance from here to here. Now, if I continued my journey, I walked 10 meters back that way, and then I walked 5 meters back this way, I would finish where I started. Now, the distance I've walked would still be 30 meters. 10 plus 10 plus 5 plus 5 is 30. But if you think about it, the displacement is a vector equivalent to distance, and so the displacement is literally the line going from start to finish. So my total displacement would be 0. So when you add vectors together, if you draw them out and you end up where you started off, then the total resultant, whatever vector it is, whether it's acceleration, velocity, displacement, or forces, if you end up where you started, then your overall resultant is 0. So we go back to this particular situation here.
Period 4 begins.
So here I've got my slope, and I've identified my 3 force vectors. So all we really have to do is put them end to end. So at the moment, I've shown my sort of free body diagram showing all my forces sort of acting and the location where they're acting. But what I do is I take my forces and I just put them end to end. Well, the first force, the one that's going to be the largest, is going to be the weight, which is vertical. Now I draw this quite faintly to start with. Now, if I think about it, I've got my force, my friction force, which is 30 degrees from horizontal. So I happen to have my set square here, so I can draw a line 30 degrees from horizontal, 30 degrees above the horizontal in this direction. So that would be my friction, that would be the direction of my friction force. And if I think about it very, very carefully, I could then have my perpendicular reaction force. And that's going to be, well, if that's 30 degrees from horizontal there, then that's going to be 30 degrees from vertical. So I could draw my line 30 degrees from vertical. I could draw it something like, let's try and get this as close to correct as I possibly can. Something like that. Okay.
Gary, could you please explain? Could you please explain the 30 degrees vertical thing again?
Yeah, sure. That's what I'm here for. Thank you for asking. Right. So here, this slope we've said is 30 degrees from horizontal. It could be 1.6 degrees. It could be 20 degrees, whatever angle it is. But I've said 30. Why? Because that's the angle of my set screen. It makes my life a lot easier. So if we look at this carefully, then we've got an angle of 30 degrees, yeah? Now, we want to work out what angle this is. If we think about it, that is the same as this, but rotated by 90 degrees. So if I've rotated F by 90 degrees, I can rotate my set square by 90 degrees. And you can see that that is 30 degrees from the vertical. Okay, I'm just getting the directions sort of correct here to start off with, because what I've ended up with are the 3 vector arrows end to end drawn in at the right angle. This is really just to demonstrate this. Hopefully you can spot straight away that this angle here is the 30 degree angle. Okay, you could even measure it, I suppose. But that's a 30 degree angle. That is a 90 degree angle, or a right angle. So what's happening here is I've got my line here, which is the weight of the object, the weight of that block of wood on there. I've got my friction force acting upwards. And I've got my perpendicular reaction force acting right angles to the ramp, or to the slope, or to the inclined plane. So I'm just going to call that R for my reaction force. So what you do then is you can actually work out what the forces are. So for example, I want to work out what my friction force is. Well, if I know the mass of the block, if I said the mass of that object was 10 kilograms, then I know its weight is going to be 10 times 9.81, because that's what G is. You assume it's 9.81 unless you're told otherwise. So that's 98.1 newtons. That's the weight of the object. So if I want to work out F, I know the hypotenuse of my triangle. This is a right angle triangle, especially if I turn it this way around. This is my right angle triangle. Okay. So we know that this is the hypotenuse of the triangle. We know that this is the opposite, because it's opposite to the angle. We know that this is the adjacent. So we're using some very standard trigonometry. So if we're using that standard trigonometry, we know a good way to remember it, for those of you who are not too sure, not everyone knows about this one. The way I remember it at school is SOHCAHTOA.
Gary?
Yep.
On your diagram, on your original diagram,
Yep.
frictional force is 30 degrees to the horizontal.
That's correct.
But when you drew it on the bottom one, it's 30 degrees to the vertical.
What, the friction force?
Yeah.
This is horizontal. This is my 30 degree angle. That's horizontal, isn't it?
Oh, I understand now.
Okay. That's all right. No. It can be confusing. That's why I'm going over this so carefully, because it's so easy to just sort of not to not quite get part of it. You've got to kind of get used to being able to rotate things in your mind. It's not easy. It's not easy, and I'll be the first to say that. So, whoops, sorry, I'd lost my screen there for a second. So what we're doing is we're using SOHCAHTOA. Okay, always remember it's SOHCAHTOA. So here the sine of the angle is opposite over hypotenuse, cosine is the adjacent over the hypotenuse, and the tangent is opposite over the adjacent. This is the one that we want to use because you've got the opposite. We want to work out the opposite. We know the hypotenuse and we know this angle theta. So we know that sine theta is the opposite over the hypotenuse. So the opposite is F. The hypotenuse is mg. And it then becomes pretty trivial. We say that we rearrange it to make F the subject. F is equal to mg times the sine of theta, which is equal to, well, we said mg was 9.98.1 multiplied by the sine of 30 degrees. Okay, and you just use your calculator. As I said before, one of the things I always mention whenever I'm doing anything to do with trigonometry and physics, on your calculator, and I'm just going to zoom in a little bit here. On your calculator, let's get it back into focus. There we go. There is here the little symbol D, and that D is for degrees mode. Okay. Whoops. So you can actually change the mode from degrees to radians, which you will use certainly if you're doing something like science maths, and certainly if you're doing pure maths, you'll probably come across it as well. It's a different unit for angle called a radian. The one you're probably never going to come across is what is it? Is gradients. Where gradients are basically, there was an attempt to try to make a metric measurement of angle, but it just never caught on. So you must always make sure that you've got your calculator set to D degrees. Okay, just a little aside there. So we're then putting in the calculation. So it's literally 98.1 multiplied by the sine of 30 degrees. And we end up with 49.05. Okay, just going to zoom back out. Sorry if this is making anybody seasick. There we are. So that's 49.05, which we've only got two or three significant figures here, so we should really say 49 degrees. That'll do nice. Sorry, 49 newtons. And that'll do nicely. Okay, so that's how you go about a question like that. It's not always obvious, but if you put your vector arrows end to end, then what you'll end up with is a way of is basically a bit of geometry that you can use. I'm going to show you another example here.
Sorry.
Yep.
Does it mean that the angle of the frictional force to the horizontal is always the same angle that the reaction force is at to the horizontal?
Sorry, the angle between the reaction force and the friction force.
Does it mean that the angle between the frictional force and the horizontal is always the same angle as the between the reaction force and the vertical?
Yeah, I mean, if you think about it, if that's at 30 degrees, then that's got to be at 30 degrees, because even if I reduce that angle, if I went down and made that horizontal, that's still at right angles. That is actually a right angle. That's 90 degrees. Yeah.
Okay.
So it's rotated by 90 degrees.
All right. Thank you.
Okay. Now, if I take you through another example, another worked example, a very popular one. Imagine you've got like a high wire that people are balancing on. So let's stick with 30-degree angles because they're very, very convenient for calculations. So if this one's at a 30-degree angle to here, I'm going to do exactly the same. here. Now, imagine you've got 2 fixed points and you've got an object. Okay, sort of on a wire. Now it's caused the wire to sag a little bit to 30 degrees. So I'm just going to give these values here. It could be any angle, but I'm just doing this because it's more convenient. Now, if we think about it, if we have a birdie sat on the wire and its weight, well, let's say the weight is equal to 1 kilo, well, mass is equal to 1 kilogram or so. Let's say 10 newtons. It just makes the calculation a little easier. Now, what I could do is I could try to calculate the tension in these two wires. Now, the first thing you're going to notice straight away is because it's symmetrical, you're probably going to notice you can predict that they're both the same magnitude of tension. But if it's in equilibrium, we can do exactly the same as we did before. So what I can do is I can put my arrows end to end. But this time I'm going to draw it to scale, because you can see here that if I put my vector arrows all end to end, I would not have a right angle triangle. And where you don't have a right angle triangle, the geometry can be a little bit trickier. So one of the methods you can use, I'm going to show you method 1 first. One of the methods you could use is to actually draw a scale diagram. Well, I'm going to make each square here to be exactly 1 Newton. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we are. So that is my 10 newtons. Now I could draw my because I've got my arrow going downwards here. From the end of that arrow, I'm looking for this arrow here. So we putting our force vectors end to end. So if I did a 30-degree angle here, let's say, here we are. I don't know how long it'll be, so I'm just going to draw it very faintly. And then somewhere along here, I've got another one 30 degrees to the horizontal in the other direction. Oops, like that, I suppose. No, hang on. What am I doing? That's it. Okay, so there's my horizontal. And I'm going to draw a 30-degree line going from, which will end up with an arrow that will end up at the top, up here. Obviously, with different angles, you may have to use a protractor, which is why I always tell you should have a protractor with you in exams. There we are. So I'll draw it straight away. Well, I know that if it's in equilibrium, then all of these arrows placed end to end will line up. And it just helps to label them. So the one in this direction, that's T1. The one in this direction, that's T2. Okay. Now, those of you with good spatial awareness will recognize this as an equilateral triangle. And therefore, you can predict that T1 and T2 are exactly, could be exactly 10 of these squares across. Well, each square on my scale is ½ centimetre. So I reckon if this is 5 centimetres, that's 10 squares. So that would actually be 10 newtons. And the same with T2. You measure it, you can physically measure it. If you put the arrows end to end, you physically measure it. What's exactly 5 centimeters, which is on the scale 10 newtons. So you can actually work out the resultant using your value for for your weight and drawing a scale diagram. But the upside of that is, if you've got a non-right angle triangle, it makes the calculation far easier. The downside of it is simply that if you get it wrong, if you mismeasure something, then you get the whole question wrong. So it's what we call swings and roundabouts. There are pros and cons to it. Your mitigating circumstances in there, of course, are that, I remember, I'm assessing you on your ability to do the physics. So when you're doing your final exam, when you're doing your exam in a couple of weeks' time, you'll realize that as long as you show the correct method, you'll get most of the marks. You might not get the final mark for the answer, but you'll get your method marks if you show your method. That's one method. That's the scale drawing method. The other way to actually work this out, to work out the tension in the two strings, is to use some trigonometry. I told you before that all vectors have got right-angled components which are independent of each other. So, for example, T1 has a vertical component and a similar horizontal component. And likewise with T2. That's the horizontal component, it's supposed to be a horizontal line. And there's your vertical line. Okay. So if I want to work out the exact, if I want to work out the tension in each of these two wires, then all I've really got to do to start off with is actually start by just resolving linear forces. The first thing I realize, of course, is that these two horizontal components have got to be equal and opposite, otherwise it wouldn't be an equilibrium, because all the forces in all directions equal 0. So these two forces are equal and opposite. So really, I'm only really concerned, just bear with me, pen stopped working, there we are. So I'm going to call this T2V, T2 vertical, and very unimaginatively, I'm going to call this T1V, okay? T1 vertical. Now, if you think about it, if we added together all the forces, we've got the birdie here, 10 Newton force, acting downwards, then you've got two forces acting upwards. So T1V plus T2V is going to be equal to the weight of the bird, okay? So if that's the case, we can then start to work out what that is. Well, if we've got T1V here, if I draw it as a vector here, that is the same as that. And that is still 30 degrees, okay? And the same up here, okay? So I can start to work out the horizontal and vertical component, the vertical components of these two wires, okay? So T1V is going to be, well, that's the opposite. So that's going to be T sine theta, T1 sine theta, plus the vertical component here, which is T2 times sine theta. It's going to be equal to mg. Okay. So because it's symmetrical, you can actually work out, you can actually see that T1 and T2 are going to be identical. So if you have T1, so we're just going to call that the tension, okay? So if that's going to be the tension, we know that that's going to be T sine theta plus T sine theta. In other words, 2T sine theta equals mg. Theta is 30 degrees. So we end up with 2T equals mg over sine theta. Okay, so therefore T is equal to mg over 2 sine theta. And then we just substitute. Well, the mass times gravity we said before was exactly 10 newtons. We just gave it a nice convenient number. 10 divided by 2 times the sine of 30 degrees. Alexa, What's the sine of 30 degrees?
The sin of 30 degrees is 0.5.
That's the other reason why I use 30-degree angles so much, because the sine of the 30-degree angle is 0.5. It's very convenient. So 2 times 0.5 is going to be 1. So T is going to be 10 newtons. So the tension in each wire is 10 newtons, which matches exactly what we've got here. So you do have to be aware of the fact there are different methods. Basically, if you have a situation where you don't have a right angle triangle when you're resolving vectors, it is nearly always acceptable to do it by scale drawing. But if you do have a 90-degree angle involved in your work, then really and truly you need to do it by calculation. If you don't have a protractor, or you just don't like the scale drawing method, you can work it out mathematically if you take the right angle, the horizontal and vertical right angle components. Okay, does that make sense so far?
Gary, do you mean like if you have vectors at 90 degrees, the best thing to do is just to use Pythagoras?
Yeah, I mean, if you've got the typical sort of equilibrium situation is where you have vectors where you've got 3 vectors and 2 of them are at 90 degrees to each other, and it's an equilibrium. In which case, you've got a 90-degree triangle. If you've got a 90-degree triangle, you can use basic trigonometry, or including things like Pythagoras theorem, to work out resultants and work out angles and so on. Depends upon what you're working out. So you've got to kind of use your judgment. But as I always say, it never hurts to draw a diagram. Hang on, oops. Try and find my original page here. So, for example, when you have your, if you go back to our original example here, where you have your slope and you've drawn your arrows on there. Sometimes the arrows are drawn for you. Sometimes the question might ask you to draw them. If you then put all the vector arrows end to end, still pointing in exactly the same direction as they were, but they're end to end. If you put them end to end, then you get a picture. Yeah, you can see the geometry that you've got to use. If when you do that, you realize you've got an exact right angle, then you know you're using right angle triangle trigonometry. If you haven't, then you know you're going to have to do scale drawing or work out vertical and horizontal components of all your forces. It is quite a nuisance to do that, but it's possible. The other thing to sort of point out here is, even if you're doing it by calculation, I always recommend drawing the triangle. You don't have to draw it to scale, but just drawing that the sort of your force diagram, so that you can see what's going on. For example, you might not realize that F was equal to mg sine theta from this diagram, unless of course you're working it out, unless of course you're working it out in your head, or you've memorized the formula. But it makes it a lot easier to see if you draw a triangle. Okay, well, if you work visually, I tend to find that people who work visually in physics, if they draw diagrams, it makes their lives a lot easier. Okay. Any questions so far?
Yes, I have a question.
Yep.
It's about the drawing method.
Yeah.
Yeah.
Yep.
So we have the weight of the bird.
Yeah.
And then T1 to the right.
T1 off to the right. Yeah.
Yeah, but I don't understand how we come about T2 going like.
Well, you can see T2 is going off to the left, isn't it? You see that?
Oh, okay.
Yeah.
Yeah.
So all I've done is,
Yeah.
is instead of putting it down over here, I've put it over here to complete a parallelogram. So I'm putting the point is I put my force arrows, my vector arrows, end to end. So the same direction, but they're not in the same location, because here we're showing the forces and where they're acting. What we're trying to do here is we're adding the forces together. So it's a slightly different diagram. That's the bit that confuses a lot of people. They get very mixed up with that. But basically, just draw your arrows end to end, and it can help you to do the calculation. However, as I said before, with scale drawing methods, I would strongly recommend that you don't use scale drawing unless you don't have a 90-degree triangle somewhere. For the simple reason that obviously calculation method is going to be more precise, is likely to be more accurate.
Yes.
But sometimes the calculation method can be a bit challenging if you're trying to use more complex geometry. But in terms of the maths required for physics, certainly at UFP level and indeed at A level, it's usually a fairly basic level of maths. It's GCSE plus a little bit more, possibly. So that's, so you're not expected to do anything that is sort of really strictly sort of high level A level maths or anything like that. Okay. Anybody got any more questions? We've got about 10 minutes left by my reckoning. Anybody got anything else they want to ask about the exam or about a topic or?
Gary, can you explain me the impulse, please?
Impulse. Impulse is quite a simple thing. Impulse is literally the same thing as a change in momentum. It's the same thing. It's defined as a change in momentum. Which is why on Star Trek they refer to impulse engines, because the engines are designed to change the momentum of the Starship Enterprise or Discovery, or whichever series you like watching. So it's literally a change in momentum. So if we think about it, the impulse is going to be delta mv. Mv is mass times velocity, which is momentum. So if you imagine you're going from two different momenta, the change in momentum, the impulse would be m. I suppose it would be mv minus u. Okay.
Okay.
So if that's the case, just to prove the point that it is a change in momentum, and it is related also to forces, if we think about it, the rate of change of momentum is going to be force. Okay, which is the change in momentum divided by time. And we know that V minus U over T from our Suvat equations is going to be the acceleration. So if that makes sense, we know that that would be F equals, well, it's going to be M times A. Okay. We could also spin off from that. That's a spin off in one direction. The other spin off direction we could take here is to remember that the change in momentum, or the impulse, is equal to force times time. Okay. All I've done is rearrange it to make Ft the subject here. Okay. So those are two particular spin-offs from impulse, but the whole idea basically is that the impulse is the change in momentum. The confusing bit is actually the units. Because it's a change in momentum, it is perfectly acceptable to use kilograms meters per second. However, it is also acceptable because the change in momentum or impulse is force times time. It's units of force multiplied by units of time, Newton seconds. And that is equally acceptable, but really only in the case of situations where you're changing momentum. If you're not changing momentum, you're just calculating a momentum, that's the unit you should use. But if you're calculating a change in momentum as a result of a force, then that's the unit you should use. At the end of the day, although that is something you should do, in a real foundation level paper, you would probably not be penalised for using this when you should have used this. You probably won't be penalised for that. You'll still get the unit mark if it's available. So don't worry too much about it. But it's just if you see either unit, it's not a mistake. These are actually dimensionally speaking exactly the same, because you know that a Newton is force times acceleration, or 1 kilogram meter per second squared. Okay, multiplied by seconds, then that means that 2 cancels to a 1. So it's kilograms meters per second. It's exactly the same. So a lot of people go, which one's right? Well, they're both right, really. Any other questions?
Thank you.
Anything at all from anyone? Anything at all?
I actually not understand properly projectiles.
Right, projectiles. So it's a good question. Projectiles, the basic rule about a projectile operating in gravity is if you imagine a particular, let's choose something rolling off a cliff. If you've got a projectile being fired horizontally with a velocity v, okay, as time goes by, it will follow a parabolic path. Now, if you look at its parabolic path at any particular point, if we ignore air resistance, and with most projectile questions we do, usually with a projectiles question, you ignore it, and then it says what happens if you have air resistance, in which case the range is less because there's more air, because it's slower. So now what happens here is obviously when this is first launched, this has a horizontal velocity v, okay? That horizontal velocity stays the same no matter where you are in that particular sort of trajectory, okay? So what happens as a result of that is basically the direction of motion of this projectile is defined as the resolution of 2 vectors. Bear with me, I'm just going to scribble again on my scrap paper. There we are. It's the resolution of 2 vectors. Okay. So basically, the final sort of velocity of the object has a horizontal component which stays the same, and a vertical component which changes. Obviously, that's going to increase because we're going to accelerate downwards at 9.81 meters per second squared, or meters per second. So it stands to reason that the vertical velocity is actually given using a CVAT equation. Well, that's going to be u plus a t, for example. So if that VV is u plus a is uv, which is the initial vertical velocity, plus at, and that a is the acceleration due to gravity g, then you can actually work out the final, the actual final vertical component of the velocity of the object. So what happens is you can work out all sorts of things, but basically the whole idea is meant to be with projectiles is you're trying to do calculations based on the fact you've actually got 2 sets of calculations. So we've got one which is the vertical sort of part of the calculation, which is using constant acceleration. So for example, if I wanted to know how far vertically something would fall, I'd say it was S, which is the vertical displacement, is equal to, let's say, well, if U is 0, it'd be a half GT squared, let's say. Now, if I knew that distance, because that's the vertical component of its displacement, okay, then if I knew that and I knew G, I could work out how long it takes to fall. And if I work out how long it takes to fall, well, that would be 2 times SV over G, square rooted. It's just a rearrangement. If I know that, and I take my vertical, I've taken my vertical sort of component there, I also know that this, horizontally speaking, it's traveling at a constant velocity. So I'm using a basic idea that if I've got a distance, it's going to be my velocity times time. And that's going to be the horizontal component of velocity, of course. So if that makes sense, if we think about it, if we look at this projectile, want to work out how far it's traveled, say, from there to there, okay, all we've got to do is work out the time it takes to fall from here to here. It actually doesn't matter that it's moving forwards. As I said before, because the fact that it's forward motion, its horizontal motion has no effect on its vertical motion, which a lot of people get very confused by. There's an experiment which is called the monkey and hunter, which is where the idea is meant to be that you've got sort of a gun and you've got a monkey. Can't draw monkeys. Hanging off a branch. Okay, oops, hanging off a branch. Now, if you've got a rather pathetic gun, we know that the bullet will follow a trajectory. So the monkey doesn't know this. So the monkey sees where the gun's pointing and thinks, well, if I let go now, then the bullet should just fly over my head because I'll have fallen a certain distance. But what actually happens is that the vertical distance fallen in the same time for both the monkey and the bullet is exactly the same, because the horizontal motion has no effect. So the monkey still gets shot. Not very nice, but it's a very, very traditional old demonstration. Apparently we're not allowed to use real monkeys anymore though. So where were we? Yeah, so I wanted to work out this horizontal distance traveled. Well, I know my my horizontal velocity because that might be given in a question. So all I've got to then do is work out the time. So the time is exactly the same time as the time it takes to go from here to here. So that's this time here. So I can substitute it in. Well, I can say it's VH multiplied by the square root of 2 times the vertical velocity, or the height, over G. There we go. So you can work it out. Now, you're not expected to memorize that formula, but what you can do is you can work it out. Okay. Now, most projectile questions in foundation level physics, because it is slightly more straightforward than A level, they tend to be very, very simple calculations. So you would be kind of guided through it. As I said, a lot of the trajectory questions seem to be, projectile questions seem to be graphs of one description or another. Okay. Everyone all right with that?
Okay, thank you.
Okay, right. Well, tomorrow morning at 9:30, I will go online again and I'll take you through that 5th practice paper. Okay, and that will sort of see us through to half term. Obviously, your half-term holiday is going to be your half-term holiday work is really just going to be get your head in the books and revise, really learn your stuff. What I'm seeing with the exams is where people are falling down. It's often is a little bit of revision needed. It's a little bit of sort of just learning the stuff. Okay, I will see you all tomorrow morning. Have a good day.